Alright, LeetCode 191, number of 1 bits. You're given a positive integer n. Count how many ones appear in its binary representation. That's the whole problem. Just count the set bits. For example, 13 in binary is 1101. 3 of those digits are 1s, so the answer is 3. The obvious approach checks every bit position one by one. Loop 32 times because that's how many bits are in an integer. Shift right each time, check if the last bit is 1. That works, but it always examines all 32 positions even if the number only has 2 set bits. We're wasting time on all those zeros. Here's the trick. It's called Brian Kernighan's algorithm. The expression n bitwise and n minus 1 removes the rightmost set bit from n every single time. So you keep applying this operation until n hits 0 and the number of iterations equals the number of set bits. But why does n and n minus 1 actually remove the rightmost set bit? When you subtract 1 from a binary number, the rightmost one flips to 0 and all the zeros below it flip to 1s. Everything above stays the same. When you AND the original n with n minus 1, that rightmost one cancels out. The bits above it survive because they didn't change. Each step knocks out exactly one set bit. Let me walk through this with n equals 13. In binary, 1101. Count starts at 0. First iteration. N is 1101. Subtract 1 to get 1100. The rightmost one sits at the very last bit, so it flips to 0 with nothing below it. And them together. 1101 and 1100 gives 1100. That rightmost bit is gone. Count becomes 1. Second iteration. N is now 1100. Subtract 1. That gives 1011. The rightmost one is now at position 2, so it flips. The 2 zeros below it flip to 1s, and them. 1100 and 101. 1 gives 1000. Another set bit cleared. Count becomes 2. Third iteration. N is 1000. Subtract 1 to get 0111. The only remaining one flips, and the 3 zeros below all become 1s. And them. 1000 and 0111 gives 0000. N is now 0. Count becomes 3. N is 0, meaning there are no set bits left to remove. The loop exits. Return 3. Runtime is big O of k, where k is the number of set bits. We loop once per 1 bit instead of checking all 32 positions. Worst case, every bit is a 1, so k is 32. But for sparse numbers with just a few ones, this finishes much faster. Space is big O of 1, just a counter variable. Here's the full code. Found this useful? Master key interview patterns at AlgoMonster and land your dream job.